The morning of December 16, 1944, somewhere in the Ardennes forest. Snow drifted across the Belgian landscape as German troops overran an American ammunition depot. Among the thousands of shells stacked in wooden crates, something caught the eye of a Wehrmacht ordnance officer. These shells looked different. The fuses screwed into their noses were not the familiar brass cylinders they had seen before. These were strange, complex, almost delicate-looking, with what appeared to be tiny glass components visible through small openings in the metal housing. Within hours, crates containing 20,000 of these mysterious fuses were loaded onto trucks and dispatched eastward, back across the German border. They arrived at testing facilities where the Reich's best weapons engineers waited to examine them. The Germans had been encountering something terrifying in the skies above their positions. American artillery shells that exploded with uncanny precision above ground level, turning trenches and foxholes into death traps. Shells that detonated near aircraft without direct hits, shredding planes that should have escaped unscathed. Now they had captured thousands of examples of whatever was making this happen. The engineers at the testing facility began their examination with methodical German thoroughness. They weighed the fuses. They measured them. They carefully photographed them from every angle. Then, with surgical precision, they began to disassemble the first sample. What they found inside should have changed everything. This is the story of how German engineers tested America's most closely guarded secret weapon and reached a conclusion that doomed the Luftwaffe. It is a story about the dangerous difference between seeing technology and understanding it, about how the best minds in German weapons development held a working miracle in their hands and convinced themselves it could not possibly work. The technology they were examining had cost America more money than the Manhattan Project would eventually spend. Over 22 million of these devices would be manufactured before the war ended, assembled by 110 factories employing thousands of workers who had no idea what they were building. The fuse represented one of the three most critical technological breakthroughs of the entire war, alongside radar and the atomic bomb. And the Germans were about to dismiss it as impossible. To understand why, you must first understand what made the proximity fuse such a revolutionary development. Before this invention appeared in American arsenals, anti-aircraft gunnery was a brutal exercise in mathematical prediction and blind hope. A gunner firing at an aircraft had two options, neither of them good. He could use a contact fuse, which only detonated if the shell physically struck the target. The chances of a 3-inch diameter projectile hitting a fast-moving aircraft at altitudes of 15,000 feet or more were vanishingly small. Or he could use a timed fuse, set to explode at a predetermined moment after firing. Timed fuses required the gunner to accurately predict where the aircraft would be several seconds in the future, calculate the shell's flight time to that point, manually set the fuse before loading, and fire with split-second timing. If any variable was wrong, the range estimate, the altitude calculation, the aircraft's speed, the wind conditions, the shell would explode harmlessly far from its target. Against modern aircraft capable of 300 miles per hour or more, with pilots executing evasive maneuvers, the hit rate was abysmal. In the Pacific Theater before proximity fuses were introduced, American ships fired an average of 654 shells for every Japanese aircraft they destroyed. 654 shells. Each weighing dozens of pounds. Each requiring manual handling by gun crews working under fire. The sheer volume of ammunition expended was staggering. The proximity fuse changed that equation completely. Instead of requiring the shell to hit the target directly, or exploding at a predetermined time, the proximity fuse detonated automatically when it sensed it was near an enemy aircraft. The shell did not need to make contact. It simply needed to pass within lethal distance. The blast and shrapnel would do the rest. With proximity fuses, American 5-inch guns required only about 9 to 6 shells per aircraft destroyed. The improvement was not incremental. It was revolutionary. Against Japanese kamikaze attacks in 1945, proximity fuses proved absolutely indispensable, turning certain slaughter into survivable combat. But the technology required to create such a device seemed impossible by the standards of 1940. The fuse needed to contain a complete miniature radio transmitter and receiver, operating on the same basic principle as radar. It transmitted a continuous signal and listened for reflections bouncing back from nearby objects. When the strength of the reflected signal indicated something was close enough to damage with shrapnel, the fuse closed an electrical circuit and detonated the shell's explosive charge. This entire system had to fit inside a metal cylinder 20 inches long and just over 3 inches in diameter. The shell itself already contained 7 pounds of high explosive. The fuse components had to squeeze into what remained. And those components had to survive conditions that seemed designed to destroy electronic equipment. When a 5-inch gun fired, the shell accelerated from 0 to 2,800 feet per second in the length of the gun barrel. That acceleration created forces 20,000 times the force of gravity. 20,000 gs. Simultaneously, the rifling grooves in the barrel spun the shell to 25,000 revolutions per minute to stabilize its flight. The tiny glass vacuum tubes inside the fuse experienced crushing acceleration and centrifugal forces that would instantly pulverize any normal electronic component. American engineers at Johns Hopkins Applied Physics Laboratory had performed an experiment to understand what these forces meant. They placed a common housefly inside an empty artillery shell and fired it vertically from a test gun. When they recovered the shell and opened it, the fly was gone. They inspected every surface carefully. Eventually they found a slight smear of organic residue on the inside wall. That was all that remained. The forces had essentially liquefied the insect. And American engineers were proposing to put delicate glass vacuum tubes containing thin wire filaments through those same forces and expect them to keep working. The British had been first to seriously pursue proximity fuses, beginning their research in 1939. Early British prototypes used photoelectric sensors that detected targets by changes in light levels. These worked reasonably well in daylight but were useless at night unless paired with searchlights. The British quickly realized that radio frequency fuses offered far greater versatility. They could work day or night, in any weather conditions, at any altitude. But the technical challenges were immense. British research focused primarily on fuses for rockets and bombs, which experienced far gentler acceleration, around 100 gs or less. When the United States entered the war effort in 1940, the British shared their proximity fuse research through the TIZAD mission, the famous technology exchange that also transferred radar and jet engine secrets across the Atlantic. American researchers, particularly physicist Mel Tuve at Johns Hopkins, saw the potential immediately but recognized that fuses for artillery shells, experiencing 20,000 gs of acceleration, would require completely new approaches. They could not simply scale down existing radio equipment. Every component had to be reimagined. The vacuum tubes were the most critical challenge. In 1940, vacuum tubes were the only way to amplify electronic signals. Transistors would not be invented for another 7 years. The standard vacuum tubes used in radios and other equipment were far too large and far too fragile for artillery shells. They shattered if you dropped a radio on the floor. The idea of firing one from a cannon seemed absurd. Yet there was no alternative. The fuse absolutely required vacuum tubes to amplify the weak reflected radio signals and trigger detonation. Researchers began testing commercial miniature hearing aid tubes, which were already much smaller than standard radio tubes. They mounted these tubes in metal blocks and dropped them off buildings to simulate impact forces. Surprisingly, many survived. They fired bullets at tube-filled metal blocks. Some tubes survived that too. They built a vertical test gun that fired shells straight up, allowing them to recover the shells after they landed. The tubes inside, properly cushioned, sometimes remained functional even after experiencing thousands of gs. The breakthrough came from understanding how to protect the tubes. Engineers embedded them in blocks of special plastic compound and coated everything with wax. This potting technique prevented the glass envelopes from shattering and kept the delicate internal elements from breaking loose. The tubes were made even smaller, about the size of the eraser on a pencil, and every internal component was redesigned to withstand extreme stress. Wire filaments were wound more tightly. Support structures were strengthened. The glass itself was specially formulated for maximum toughness. Even the other electronic components required complete redesign. Resistors, capacitors, batteries, all had to be miniaturized and ruggedized. A special battery was developed that could operate in temperatures from 100 degrees Fahrenheit to 50 below zero, and survive being spun at 25,000 revolutions per minute. The entire assembly contained about 130 individual parts, each specially manufactured to tolerances that had never been required before. By August of 1942, the team at Johns Hopkins had produced what they believed was a working design. The test took place on Chesapeake Bay aboard the newly commissioned light cruiser USS Cleveland. 3 radio-controlled drone aircraft would serve as targets. The test was scheduled for 2 days. The Navy expected it would take hundreds of rounds to destroy the 3 drones, based on experience with timed fuses. The actual test lasted less than 1 day. Cleveland's gunners destroyed the first drone with the very first salvo of proximity-fused shells. A second drone was sent up. It was shot down just as quickly. A third was requested. The test coordinators refused to send it up. They normally planned on each drone surviving hundreds or even thousands of rounds. 3 drones destroyed with just 4 salvos was so far beyond expectations that the test was immediately terminated and mass production was ordered. The United States Navy introduced proximity fuses to combat on January 5, 1943. The cruiser USS Helena was operating off Guadalcanal when Japanese dive bombers attacked. Lieutenant Red Cochran, commanding Helena's aft 5-inch battery, opened fire with the new fuses. His second salvo destroyed one of the attacking aircraft without a direct hit. The shell simply exploded near enough for shrapnel to fatally damage the bomber. Within months, proximity fuses had spread throughout the Pacific Fleet. The effectiveness was dramatic and immediate. Japanese pilots who had learned to evade conventional anti-aircraft fire found themselves facing an entirely new threat. Shells that exploded precisely when they passed near aircraft, requiring no direct hit, no perfect timing, just proximity. The psychological impact was profound. What had been a predictable pattern of flak bursts at fixed altitudes became an intelligent, responsive defense that seemed to anticipate every maneuver. But the Pentagon absolutely forbade the use of proximity fuses over land in Europe. The fear was simple and understandable. If a fuse fell into German hands as an unexploded dud, German engineers might reverse-engineer the technology and develop their own proximity fuses. Germany possessed excellent scientists and advanced electronics industries. If they cracked the secret of the proximity fuse and deployed it against Allied bombers, the results would be catastrophic. American heavy bombers were already suffering grievous losses to German anti-aircraft fire using timed fuses. German 88mm guns, firing shells with time delay fuses set by sophisticated mechanical predictors, created defensive boxes of exploding steel that Allied bomber crews called flak. The Germans calculated that destroying a single American bomber with timed fuses required approximately 4,000 shells at a cost of 100 Reichsmarks each. That was enormously expensive in ammunition and production capacity, but it worked. German flak was deadly enough with timed fuses that bomber crews had only a 50% chance of surviving their tour of 25 missions. If Germany acquired proximity fuses, the mathematics changed catastrophically. American intelligence estimates suggested that German anti-aircraft effectiveness would increase by a factor of 3 to 4 times. Instead of 4,000 shells per bomber destroyed, perhaps only 1,000. The loss rate would become unsustainable. The entire strategic bombing campaign, which was grinding down German war production at enormous cost in men and machines, might become impossible. So proximity fuses remained restricted to naval use over water, where unexploded shells would sink harmlessly to the ocean floor, taking their secrets with them. This restriction held through 1943 and into 1944. Despite the devastating effectiveness proximity fuses demonstrated in the Pacific. In July 1944, when German V-1 flying bombs began terrorizing London, the restriction was partially lifted. British anti-aircraft batteries along the English coast were equipped with American 90mm shells fitted with proximity fuses. The results vindicated every claim made for the technology. In the first week, coastal batteries destroyed 24% of all V-1s engaged. By the fourth week, that figure had risen to 7 to 9%. On one particularly successful day, British gunners engaged 104 incoming V-1s. Only 4 reached London. Still, the Pentagon refused to allow proximity fuses in field artillery over land in Europe. General Dwight Eisenhower protested vehemently. He could see what the weapon could do against flying bombs. He wanted it against German troops. The Pentagon remained adamant. Then came December 16, 1944. Germany launched what would be their last major offensive on the Western Front. 24 divisions, more than 200,000 men, supported by nearly 1,000 tanks, smashed through American lines in the Ardennes forest. It was the Battle of the Bulge, Hitler's final gamble to split the Allied armies and force a negotiated peace. Colonel George Axelson commanded the 406th Artillery Group, positioned to support American cavalry units near Monschau, Germany. His unit had recently been issued proximity fuses with strict orders not to use them unless specifically authorized. When the German offensive erupted and his cavalry was in danger of being overrun, Axelson made a command decision. He ordered his gunners to fire proximity-fused shells. The results were immediate and devastating. German troops advancing through the forest had felt safe from conventional artillery because the bad weather prevented aerial observation for adjusting fire. They moved in the open, confident that American gunners could not see them to aim accurately. The proximity fuses did not require optical observation. They detonated automatically 30 to 50 feet above ground, precisely the height to maximize shrapnel coverage over the widest area. German soldiers in trenches, behind logs, in foxholes, places that would have protected them from shells that exploded on impact, were torn apart by fragments raining down from above. There was no defense. No cover worked. The fragments even penetrated log-reinforced bunkers. 3 days after the offensive began, Eisenhower received formal permission to use proximity fuses throughout the European theater. 200,000 shells had already been stockpiled in anticipation of eventual approval. They were immediately distributed to artillery units across the front. General George Patton would later write that the funny fuse won the Battle of the Bulge. He described catching an entire German battalion attempting to cross the Sauer River. One American artillery battalion fired a concentrated barrage of proximity-fused shells. 702 German soldiers were killed by actual count. Patton concluded that when all armies acquired such weapons, entirely new methods of warfare would be required. The German prisoners who survived these bombardments described the experience as devastating and inescapable. The shells exploded overhead with frightful precision. Shrapnel came from above. Traditional defensive positions offered no protection. Some units experienced what amounted to mutiny, with soldiers refusing orders to leave their bunkers during artillery attacks. They had developed tactics for surviving conventional artillery, but this was something new, something against which their training and experience offered no defense. And then, sometime during those first chaotic days of the offensive, German forces overran an American ammunition depot and captured 20,000 proximity fuses. The captured fuses were immediately transported to German research facilities. The Reich's finest ordnance engineers gathered to examine them. These were not amateur tinkerers. They were highly trained scientists and weapons specialists, many with advanced degrees in physics and electrical engineering from prestigious German universities. Germany had been working on proximity fuse development since the early 1930s. They had explored acoustic fuses that triggered on engine noise, electrostatic fuses that detected electrical fields around aircraft, photoelectric fuses that sensed changes in light, and radio frequency fuses similar in principle to what the Americans had built. German researchers had developed more than 30 different proximity fuse programs by some estimates, possibly as many as 50 distinct approaches. But none had entered production. None had been used operationally. The technology that was devastating German forces from the sky remained, to German engineers, a theoretical possibility not yet reduced to practical reality. Now they held 20,000 working examples. The engineers carefully disassembled the first fuse. What they found was simultaneously remarkable and disturbing. The device was ingenious. Miniaturized far beyond what German industry had achieved. The vacuum tubes were impossibly small, smaller than anything in German production. The entire assembly was extraordinarily compact, fitting into a space that seemed inadequate to house a functional radio transmitter and receiver. The engineers traced the circuits. They identified the transmitter section, the receiver, the detector that sensed when reflected signals indicated proximity to a target. They examined the battery, the safety mechanisms, the detonator circuit. Everything was there. Everything was real. This was not propaganda or deception. The Americans had actually built a working radio proximity fuse that functioned inside an artillery shell. The question was how. How had the delicate vacuum tubes survived being fired from a gun? German engineers knew precisely what forces were involved. They had been developing artillery for decades. They understood that artillery shells experienced acceleration forces that destroyed almost any delicate mechanism. Their own research had concluded that vacuum tubes simply could not survive such forces. Glass would shatter. Filaments would break. Internal components would come loose. The acceleration would pulverize any electronic device. This was not speculation. This was established fact, confirmed by decades of experience and countless failed experiments. Yet here in their hands was proof that the impossible had been achieved. The American fuses clearly worked. German soldiers were dying because these fuses worked. But German engineering doctrine said they should not work. The vacuum tubes should have been destroyed the instant the shell was fired. There had to be some explanation they were missing. The engineers examined the tubes more closely. They saw how the tubes were potted in plastic compound and sealed with wax. They saw the miniaturization, the rugged construction, the careful design. But they could not accept what the evidence showed them. Their theoretical understanding said this was impossible. The tubes could not survive the acceleration. Therefore, these must not be real proximity fuses for artillery shells. Perhaps they were fuses intended for rockets or bombs, which experienced far gentler acceleration. Perhaps the Americans were using them in some other application. Perhaps this was an elaborate deception, and the real secret lay elsewhere. The German engineers wrote their reports. They documented what they had found. They noted the sophisticated miniaturization and clever design. And then they concluded that while the fuses were interesting, they could not possibly function as proximity fuses for artillery shells fired from guns. The acceleration forces made such a thing impossible. Their own research had proven this conclusively. This conclusion was not the result of stupidity or incompetence. It was the result of being trapped by their own expertise. The German engineers knew so much about what was impossible that they could not accept evidence of what was real. They had spent years researching proximity fuses. They had tested countless designs. They had failed repeatedly to create vacuum tubes that could survive being fired from a gun. They had accumulated an enormous body of knowledge about why proximity fuses for artillery were impractical. That knowledge blinded them to the reality sitting on their workbenches. The Americans had solved problems that German engineering said were insoluble. They had developed specialized manufacturing techniques for vacuum tubes that German industry had never attempted. They had created materials and assembly methods that eliminated failure modes the Germans considered unavoidable. They had approached the entire problem from a different direction, with different assumptions and different priorities. And because the German engineers could not see how the Americans had done it, they convinced themselves it had not been done. In early May of 1945, just days after Germany's surrender, General Karl Spaatz interrogated Reichsmarschall Hermann Göring at the Ritter School in Augsburg. Göring had commanded the Luftwaffe through its rise and catastrophic fall. He knew intimately how badly proximity fuses had hurt German aviation. Spaatz asked him directly, "Have you any knowledge of a proximity fuse?" Göring responded that Germany had been developing its own proximity fuse. With the resources that remained, he estimated it would have been in production within 3 or 4 months. Just 3 or 4 months. If Germany had held out slightly longer, if the war had continued into summer, the Luftwaffe might have deployed proximity fuses against Allied bombers. But those 3 or 4 months might as well have been years. By May of 1945, Germany had no time left. The question Spaatz did not ask, but should have, was whether Germany knew about American proximity fuses earlier. Whether captured examples had been examined. Whether German engineers had studied the technology and failed to recognize what they held. The answer, had Göring known it, would have been profoundly ironic. 20,000 working examples had been captured 5 months earlier. Enough to equip German research facilities with abundant samples for study and reverse engineering. Enough that German engineers could have tested them analyzed them, and learned exactly how the Americans had solved the problems Germany considered insoluble. But the engineers never recognized what they had captured because they already knew it was impossible. The difference between American and German approaches to the proximity fuse problem reveals something fundamental about how nations organize technological development during wartime. The Americans had concentrated their effort. One primary research laboratory at Johns Hopkins Applied Physics Laboratory. One fundamental approach, the radio frequency method using miniaturized vacuum tubes. One massive coordinated production effort involving over 100 factories, all working to produce identical fuses to a single design. The Germans had fragmented their effort across more than 30 separate proximity fuse programs, possibly as many as 50 by some estimates. Each program pursued its own approach. The Graf Zeppelin Institute developed acoustic fuses that triggered on engine sound, with projects designated Stimgabel and Kranich. The Orlik Institute in Danzig worked on radio fuses called Wiesel and electromagnetic designs called Eisgrim. Rheinmetallborsig pursued an electrostatic fuse designated Kuglock, which detected changes in electrical fields around aircraft. AEG Berlin developed the Fuchs radio fuse for guided missiles. Brickman of Gera experimented with infrared detection called Roulette. Blaupunkt worked on a radio fuse designated Trichter. Donaulandisch in Vienna produced 3,000 radio fuses called Kakadu for the HS-293 guided bomb, using Doppler effect detection. The list continued through variations on photoelectric detection, capacitive sensing, and hybrid systems. Each project had merit. Each had solved some part of the proximity fuse problem. But none had solved all the problems simultaneously. None had progressed from laboratory prototype to mass production. None had achieved the integration of all the required technologies, miniaturization, ruggedness, reliability, and manufacturability into a single working system. This fragmentation was not stupidity. It reflected the structure of German military procurement, where the Army, Navy, and Air Force competed for resources and rarely shared research. It reflected the Nazi preference for revolutionary wonder weapons over incremental improvement of existing systems. It reflected Germany's increasingly desperate industrial situation, where scarce resources were divided among dozens of competing priority programs. The American approach succeeded because it concentrated effort and resources. Johns Hopkins Applied Physics Laboratory received authority to coordinate all proximity fuse research. When they determined that radio frequency methods were most promising, photoelectric research was terminated in October 1943 and those resources were redirected. When manufacturing problems emerged, 100 companies worked together to solve them rather than each pursuing separate solutions. When the fuse entered production, all factories built to identical specifications, allowing any fuse to be loaded into any shell. The German approach failed despite having started proximity fuse research earlier than the Allies, in some cases as early as the mid-1930s. Individual German programs achieved remarkable technical sophistication. The Rheinmetallborsig electrostatic fuse, for example, demonstrated sensitivity of 1 to 2 meters initially, then 3 to 4 meters after circuit adjustments, finally achieving 10 to 15 meter sensitivity with 80% reliability when fired from 88mm cannons. That fuse was reportedly ready for production when Allied forces overran the facility in 1945. But ready for production in 1945 meant it was 5 years too late to matter. The Americans had been mass-producing proximity fuses since 1942. They had fired millions in combat. They had refined the design, improved reliability, and driven costs down from $732 per fuse in 1942 to $18 in 1945. German programs that achieved technical success in 1945 were competing against a proven, mature, mass-produced American system that had already changed the character of the war. The irony becomes even sharper when you consider what the Germans could have learned if they had recognized what they captured in December 1944. Those 20,000 fuses represented not just working examples of the technology, but a complete solved problem. American engineers had already determined which approaches worked and which did not. They had solved the vacuum tube survival problem. They had developed the manufacturing processes. They had created the quality control procedures. They had integrated all the components into a reliable system. If German engineers had recognized this, they could have abandoned their fragmented research programs and focused on reverse engineering the American design. They could have studied the tube potting techniques, the circuit layouts, the mechanical safety devices, the battery design. They could have learned from American successes instead of repeating American failures. They might have compressed 5 years of development into a few months. But they never took that step because their own research told them it was impossible. They had spent years trying to build vacuum tubes that could survive artillery launch. They had failed repeatedly. They had accumulated comprehensive documentation of why it could not be done. That knowledge, that expertise, that institutional memory of failure, prevented them from seeing that someone else had succeeded. This phenomenon appears throughout the history of technology. Experts in a field often reject innovations because those innovations violate principles the experts know to be true. The Wright brothers succeeded in powered flight partly because they were not trained aeronautical engineers. They did not know that heavier-than-air flight was impossible according to contemporary mathematical analysis. They simply built what worked and refined it through trial and error. Chester Carlson invented xerography after every major corporation told him photocopying was impractical because photographic processes were too slow and expensive for document reproduction. He succeeded because he approached the problem differently, using electrostatic principles that photography experts considered irrelevant to copying. The proximity fuse represented American industrial and organizational capability as much as American technical innovation. The fuse worked because America had the industrial capacity to manufacture millions of miniature vacuum tubes to unprecedented quality standards. America had the organizational ability to coordinate over 100 factories. America had the resources to spend over $1 billion developing what was essentially a disposable electronic device that would be destroyed seconds after it was used. Germany lacked these capabilities by 1944. Even if German engineers had recognized the American fuse design and understood how to replicate it, Germany probably could not have mass-produced it. The miniature vacuum tubes alone required specialized manufacturing equipment, trained workers, and quality control procedures that German industry could not match while under sustained Allied bombing. The batteries required materials Germany could not obtain. The entire system required a level of industrial coordination that Nazi Germany's fragmented command structure made nearly impossible. Perhaps the most telling detail about German proximity fuse development appears in Göring's interrogation. He estimated Germany would have had working fuses in production within 3 or 4 months if the war had continued. 3 or 4 months. That estimate suggests German engineers had solved most of the technical problems by May 1945. They understood how to make proximity fuses work. They simply ran out of time. But 3 or 4 months was an eternity by May 1945. Germany was destroyed. Its cities were burning. Its armies were shattered. Its industrial base was wrecked. Allied forces occupied German territory from multiple directions. The war was clearly lost. A few more months would have made no difference to the outcome. If German engineers had studied those captured fuses more carefully in December 1944, if they had recognized what they held, if they had abandoned their preconceptions about what was possible, they might have compressed that development timeline dramatically. They might have had working fuses by February or March of 1945. They might have deployed them against Allied bombers in the final desperate months. Would it have changed the war's outcome? Almost certainly not. By early 1945, Germany was doomed regardless of technological developments. But proximity fuses would have made the final months far bloodier for Allied aircrews. American bomber losses would have increased dramatically. The strategic bombing campaign might have become unsustainable. Thousands of additional Allied aircrew might have died in the final weeks before Germany's inevitable collapse. The fact that this did not happen, that German engineers dismissed the captured fuses as impossible, represents one of the war's fortunate ironies. American lives were saved because German experts knew too much about what could not be done. The lesson extends beyond World War II military technology. Organizations accumulate knowledge over time. That knowledge becomes doctrine, standard practice, accepted wisdom. The accumulated experience guides decision-making and prevents wasteful repetition of past mistakes. But accumulated knowledge can also become accumulated prejudice, a rigid framework that rejects innovation because innovation contradicts what everyone knows to be true. This creates a paradox. The more expert someone becomes in a field, the more vulnerable they are to being blindsided by approaches that violate the rules of their expertise. Fresh perspectives, people who do not know what is impossible, sometimes achieve breakthroughs that experts consider absurd. But relying on fresh perspectives over expert knowledge is dangerous. For every innovation that succeeds by violating accepted principles, hundreds fail because those principles are actually correct. The Wright brothers succeeded, but thousands of other aviation pioneers crashed and died trying approaches that experts correctly identified as impossible. The proximity fuse story suggests the solution is not choosing between expertise and fresh perspective, but creating organizational structures that allow both. The Americans succeeded partly because Johns Hopkins Applied Physics Laboratory brought together physicists who understood radio theory, engineers who understood manufacturing, and military officers who understood combat requirements. Each group contributed different knowledge. Each group challenged the assumptions of the others. When vacuum tube experts said miniaturization was impossible, physicists suggested new approaches. When manufacturing engineers said production was impractical, military urgency forced innovation. German proximity fuse programs lacked this integration. Research institutes pursued technical elegance. Military offices demanded immediate results. Manufacturing companies had no input during design. Each group operated in isolation, optimizing for their own criteria without considering how their work would integrate with others. The result was 30 or more technically sophisticated programs that never cohered into a single deployable system. After Germany's surrender, Allied technical intelligence teams fanned out across the country, seeking German research facilities and interrogating scientists. They found extensive documentation of proximity fuse programs. They found prototypes of remarkable sophistication. They found research that had progressed further than Allied intelligence had believed possible. But they found no deployed weapons. No operational fuses. Nothing that had affected the war's outcome. The captured American fuses, those 20,000 examples seized in the Ardennes, were never located. They might have been destroyed during fighting. They might have been dispersed to different research facilities and lost in the chaos of Germany's collapse. They might still exist somewhere, forgotten in a storage room or private collection. Or they might have been deliberately destroyed by German officials trying to conceal how close they had come to understanding what they held. The story of the proximity fuse demonstrates that technology transfer is not simply a matter of obtaining hardware. The physical artifact is necessary but insufficient. You must also understand the reasoning behind design choices. You must possess the industrial capability to manufacture components. You must have organizational structures that can coordinate complex development programs. You must have the cultural and institutional flexibility to abandon failed approaches when better ones emerge. Germany possessed brilliant scientists and engineers. German technical universities were world-class. German industry had demonstrated remarkable innovation in fields like chemistry and precision manufacturing. But Germany's political structure, its fragmented military command, its ideological insistence on German superiority, and its deteriorating industrial situation prevented effective technology development in the war's final years. The proximity fuse represented more than electronic miniaturization. It represented American industrial capacity, organizational efficiency, and pragmatic problem-solving. Those qualities could not be reverse-engineered from captured hardware. They were systemic advantages that no amount of technical cleverness could overcome. James Van Allen, the physicist who developed the miniature vacuum tubes that made proximity fuses possible, went on to become one of America's most distinguished space scientists. In 1958, instruments he designed aboard America's first satellite, Explorer 1, discovered the radiation belts surrounding Earth. Those belts were named the Van Allen belts in his honor. His wartime work on proximity fuses was largely forgotten, classified for years after the war ended, overshadowed by more dramatic developments like atomic weapons. But Van Allen's contribution to Allied victory was arguably greater than many better-known technologies. Proximity fuses saved thousands of American lives in the Pacific by making anti-aircraft fire dramatically more effective against kamikaze attacks. They saved thousands more in Europe by making artillery more lethal during the Battle of the Bulge. They allowed smaller numbers of guns to achieve greater effects, reducing the logistics burden of ammunition supply. They changed the mathematics of aerial warfare permanently. Merrill Tuve, who directed the proximity fuse program at Johns Hopkins, returned to physics research after the war. He had spent 5 years of his career on weapons development. 5 years he considered necessary but distasteful. He was a scientist, not a weapons designer. He wanted to return to pure research, understanding the universe rather than destroying it. But he understood that the proximity fuse had been essential to victory. Sometimes scientists must set aside their preference for pure knowledge and apply their expertise to immediate practical problems, no matter how unpleasant those problems might be. The factories that produced 22 million proximity fuses during the war converted back to civilian production. Sylvania, which had employed 10,000 workers building miniature vacuum tubes at rates the pre-war radio industry could never have imagined, returned to making consumer electronics. The manufacturing techniques developed for proximity fuses found applications in peacetime products. The miniaturization experience contributed to the development of transistors and eventually integrated circuits. The proximity fuse's descendants continue serving today. Modern anti-aircraft missiles, artillery shells, and air-to-air weapons use proximity fuses based on laser ranging, radar detection, or other methods far more sophisticated than World War II radio fuses. But the fundamental principle remains identical. Detonate when close enough to damage the target. Don't require direct contact. Maximize the probability of success. The story that began with German troops capturing ammunition in the Ardennes forest ended with German engineers writing reports that dismissed what they had found. Between those two moments lay an opportunity that was never recognized. 20,000 working examples of one of the war's most important technologies sat in German research facilities. German engineers examined them, tested them, documented them, and concluded they could not possibly work as advertised. This was not a failure of intelligence. It was a failure of imagination. An inability to accept that problems you have spent years failing to solve might have been solved by someone else using approaches you never considered. A conviction that your expertise, your knowledge, your accumulated experience must be correct, and evidence to the contrary must be flawed or misunderstood. The cost of that failure of imagination is measured in lives saved. Allied bomber crews who survived the war's final months because German anti-aircraft fire remained only as deadly as it had always been, instead of becoming 3 or 4 times more lethal. Allied soldiers who survived German artillery because shells continued detonating on impact or at fixed times, not optimally above ground where they would cause maximum casualties. Sometimes the most important victories come not from what you achieve, but from what your enemy fails to achieve. The proximity fuse was a triumph of American innovation, organization, and industrial might. But it was also a triumph that German engineering could have partially negated if German engineers had been able to see past their own expertise. They could not. And so one of the great technological secrets of World War II remained a secret not because the Germans never captured examples, but because they captured 20,000 examples and convinced themselves those examples could not be real. They held the future in their hands and dismissed it as impossible. They tested it, documented it, and filed their reports concluding it could not work. And while they were writing those reports, dismissing the evidence before them, American proximity fuses continued detonating above German positions, above German aircraft, destroying targets that should have escaped unscathed. The Germans tested captured American proximity fuses. They examined them with scientific rigor. They applied all their considerable expertise. And they reached a conclusion that perfectly illustrated why expertise alone is insufficient. Sometimes you can know so much about what cannot be done that you become incapable of recognizing when someone else has done it anyway. If this story revealed something you had never considered about World War II technology and the dangerous limitations of expertise, take a moment to share your thoughts in the comments. We read every response, and your perspectives from Texas to Berlin to Tokyo enrich these conversations. Every story from this war carries lessons that resonate today, in laboratories and boardrooms and government offices where experts must balance accumulated knowledge against the possibility that established rules might not apply. Consider subscribing if you value deeply researched history that looks beyond the famous battles to examine the human and institutional factors that shaped the war's outcome. These stories matter not just as history, but as insight into how organizations succeed or fail when confronting the unknown. Thank you for spending this time exploring how German engineers held a war-winning technology and dismissed it as impossible, and how that failure of recognition represents one of the conflict's most consequential decisions that was never actually decided, just assumed based on expertise that turned out to be incomplete.